It's alive! It's alive!
That's right guys, the machine is finally alive and I can't wait to see what this machine can do. Now, if you missed the first 2 episodes, here's a quick recap to what happened in the first 2 episodes. Previously on DIY CNC KR8. Beautiful Sunday morning, and unfortunately we are in the second day of EMCO, or you can think of it as the enhanced version of a lockdown. So now is the best time to work on the electronics since we can't go anywhere, and today's episode is all about the electronics and the electrical panel. Let's go through some of the components. So this one is the main power disconnect switch, and it is rated for 16 amps. This is a very simple AC power socket that you can find in most computer casing. This is where the main AC line comes in. For thermal overload protection, I'm using a circuit breaker rated for 10 amps. As for the power distribution block, I am using Phoenix Contact's PT Fix series. These are very convenient as you can easily insert the wires from the front and you can combine multiple modules easily, just like this, together with the DIN rail adapter. So you can just easily slide this on and just clip it to the DIN rail once you're done. For the 24 volt DC supply, I'm using Meanwell's 24 volt DIN rail type power supply rated for 20 watts. So this is mainly for the safety circuit, so 20 watts is sufficient. Next up is the 3-pole Siemens contactor with a 24 volt auxiliary contact, which controls the AC supply to both the 36 volt stepper motor power supply and also the power to the spindle VFD. This piece you see right here is the surge suppressor, which suppresses the residual energy coming from the contact when it is released or disengages. For switching the contactor on and off, I am using a double push button from the brand called Hitachi. It's a Korean brand. These are momentary contacts. Okay. However, I realized the unit that I bought is actually missing an LED module here. So maybe I will look for this module somewhere in the future. But right now, I'll just use this as this will still function. This is an unbranded e-stop I'm using for my machine. I will probably print out a 3D case to house this external e-stop. It's a simple e-stop with a normally closed circuit and a normally open on the other side. For switching the VFD on and off, I am also using a selector switch from the Korean brand Hitachi. This is a 36 volt 350 watt power supply for the stepper drivers. It's from Meanwell, and this is the EMI filter I'm using for my VFD. For the stepper driver, I'm using a TB6600. You can easily buy a complete kit of stepper motors and drivers from sites like Banggood for a reasonable price. As for the CNC controller, I'm using an Arduino Uno together with Nikodem Bartnik's IndyShield. For DC 12 volt supply, I am using Meanwell's 15 watt 12 volt DC supply. So this will provide power for the Arduino and the 12 volt DC fan. This is a GRBL optocoupler board used to connect the limit switches to the Arduino to eliminate any noise coming from the spindle or any other devices. This is a 5 volt relay board which controls the 24 volt solenoid valve for the air coolant on and off. Now this is the board that converts the PWM signal from the Arduino to a 0 to 10 volt analog voltage for the VFD to control the spindle speed. As for the solenoid valve for the air coolant, I am using AirTech's 32A valve spring return. For the control panel's ventilation, I'm using a DC 12 volt brushless. Before we start doing anything on the electrical panel, let's have a look at the wiring diagram. So at first glance, this might look very overwhelming, but I'll go through with you guys. It's actually not that difficult. So on the left, you can see this is where the AC 240 volt comes in. So this will go through a circuit breaker. It's primarily for thermal overload protection. Then it fits into a power disconnect switch and goes through a power distribution block. So for this, I have one block for live, one for neutral, and one for earth. So there are 3 basic DC voltages, including the 5 volt. There will be 4. So there's one 12 volt DC power supply, mainly for providing power to the Arduino. One 24 volt power supply for the safety circuit, and one 36 volt power supply for the stepper drives. On the lower left corner, we have AC supply to both the VFD and the 36 volt PSU. And remember, the AC supply to both the VFD and the 36 volt power supply is controlled by the contactor. So in case there is a power outage, the AC power to both the power supply and the VFD will be cut off, and it can only be turned on again by manually pressing the on button or releasing the e-stop and pressing the on button. Okay, so on the VFD side, there is another on-off selector switch and also an EMI filter to filter out the noise. On the right side of the wiring diagram, we have mostly the control electronics. We have a 12 volt DC supply which provides power to the Arduino and IndiShield, and also the PWM to 10 volt converter. The 5 volt from the Arduino will be used to power the 5 volt relay, which controls this solenoid valve for the coolant and the air. For the limit switches, I am using a optocoupler which was recommended by the GRBL website, primarily to separate the noises from affecting the reading. And on the right side here, the 4 stepper drives will be hooked up to the Arduino IndiShield. Now, you might be wondering why there is a PWM to 10 volt analog converter here. So if you have a look at this circuit over here, the PWM to 10 volt analog converter actually is used to control the speed of the VFD spindle. The reason we need a PWM to 10 volt analog converter is because the Arduino is giving an output of PWM 5 volt signal, whereas the VFD only accepts 0 to 10 volt analog signal in order to control the speed. So that's why we need a PWM to 10 volt analog converter here. For the 5-volt relay, since I'll be using a solenoid valve to control the air for the coolant, and this industrial solenoid valve runs on 24-volt DC, so I'm using a 5-volt relay here, which is controlled by the Arduino to complete the 24-volt circuit to the solenoid valve. Alright, and basically, so that's about it. So before I put all the components permanently into the panel, I'll be testing a few circuits just to make sure they work before I put it in. So one of the subsystems I'll test is the safety circuit. This is number 1. And the second circuit I will test will be the spindle speed control using the PWM to 10-volt analog converter. And the last one that I'll be testing will be the control of the solenoid valve using the Arduino, which is this one over here. So this one will be the third one that I'll be testing. As for the grounding wires, all the ground wires from the stepper motors and also the VFD spindle goes directly to one central location over here. It connects to a power distribution block, and there's one wire that goes directly to the power socket in order to avoid any ground loops. Right here I have the circuit that controls the spindle speed hooked up. So this, the Arduino has a pin that controls the spindle speed. So this is the spindle control pin, which outputs a PWM signal. So that goes into this PWM to 0-10-volt analog converter, and the output from this converter goes into the VI and ground pin of the inverter, the VFD. So later what I'm going to do is I'll input the speed values from my laptop using CNC JS, and I will gradually increase the speed all the way from 3000 RPM to 24,000 RPM. To start the spindle, you have to key in M3 and set the speed with an S followed by the number in RPM. In order to stop it, you just have to press or key in the command M5 to stop the spindle. So this is pretty much it, and this part seems to be working fine. Just a couple of things to take note. If you are using this inverter model YL620-8, you have to set the dip switch here to this position in order for the frequency to scale correctly in relation to the PWM to 10-volt converter. Next up is the safety circuit, which controls the power to the stepper motors and also the VFD. So what I have here is the main AC supply coming to the circuit breaker. So right now I'm turning it on, and this is main power disconnect switch. So in order to provide power to everything, you need to switch it on. So right now you can see the 24 volt DC supply is on, and in order to start giving power to the stepper motors and the VFD and the other devices, I need to press this on button here. So immediately after I press it, the contactor is now engaged. Alright, so as soon as I press the off button, the contactor disengages. By pressing the emergency stop, I can also disengage the contactor. So once this contactor disengages, there will be no power to the VFD and no power to the stepper motors. Okay. So in order to reset the power to the VFD and stepper motors, I have to release the emergency stop button and press the on button one more time. Then only it will provide power to the VFD and the stepper motors. In the event of a power outage, for example, the contactor should disengage and it should not provide power immediately when the power comes back on until I press on the on button. Okay, perfect. So this part is working fine. The safety circuit is working as intended. So the final circuit that I want to test is actually controlling the coolant air on-off using this pneumatic valve through a 5 volt relay. Alright, so I got the Arduino hooked up to the relay, and the relay is hooked up to this solenoid valve. So right now I'm trying to send a command through CNC JS just to turn the coolant air on-off. So to turn it on, you can just key in M8 on CNC JS. So right now it's on. So to turn it off, you just need to key in M9. Alright. On and off. So this circuit seems to be working fine. So the tests for all the circuits are now complete. Does anyone have any more questions? I'll take that as a no. And before I let you go, remember, like and subscribe to my channel, or I'll be seeing you next semester again. Class dismissed. Here I was applying finishing touches, and just when I thought I had everything checked and done, this happened. The cable to the VFD control panel is just not long enough when I open up the panel. The original cables that came with the VFD was a little bit short, so this is already fixed. I soldered the extensions and extended the length of the cables, so this is solved. Okay guys, so after many weekends of working on this electrical panel, maybe more than 2 months, I finally completed the wiring for this panel. So I just want to go through a little bit on the details of this panel with you guys. So on the right side, this is where the AC main comes in, and this is the power disconnect switch. This is the exhaust fan, the 80mm exhaust fan. And on the front of the panel, we have the momentary on-off button, which controls the main power to the motors, the stepper motors and the VFD. And this is the selector switch, which controls the power to the VFD. And right here is the control panel for the VFD. Okay. I designed a additional holder just to hold the VFD in place, and this part is printed out of ASA, which is supposed to be weather and UV resistant. On the bottom side here we have all the connectors coming out. So this is a panel mounted USB 2 connector, sorry, which is IP rated for IP67. You don't have to use 4-pin, it's just that I bought a bunch of these 4-pin connectors, so I'm using a 4-pin. You need essentially only 2 pins and 1 pin for earth ground. So right now I'm using 2 pins for the signal and 1 pin for earth ground. So 3 connectors for each limit switch. And over here I'm using 5-pin GX16 connectors for all the stepper motors. Okay, 4 pins for the motor and 1 pin for the earth ground. It's how I connect the shield of the shielded cable through the 5th pin. Okay, and this is for the e-stop. And these two are the pneumatic bulkhead unions. So this is where the air goes in to the solenoid valve, which controls the air to the coolant, and this one goes to the nozzle. Okay, and for the spindle I'm using a GX20 5-pin connector, 3 pins for the 3 phases, 1 for the spindle ground and 1 more pin for the shield ground, and 1 more GX16 connector for the probe. On the right side I have a opening for fresh air to go into the panel. Okay, now let's open up the panel. Okay, it's not the prettiest arrangement, but yeah, it's the best that I can do. For the grounding of the shielded cables and everything else, all ground cables go directly to a central location, which goes back to the AC mains earth ground in order to avoid any ground loops. Also, another important thing to note, if you're using a metal enclosure, just remember to connect the ground, the casing, to the earth ground for safety precautions. You don't want to get shocked while you are touching on the enclosure, any part of the enclosure. So what I'm going to do now is to close the panel and try to hook up all the cables from the machine, and to power up this machine for the first time. I have all the cables hooked up to the electrical panel now. The power cable is hooked up to the AC main, and I double check my wiring, and most importantly I have another fire extinguisher on standby just in case. So right now, are you guys ready for this? I'm gonna power up this machine for the first time. So here it goes, switching on the power. Fan is on, and whew, great, nothing tripped, nothing exploded, looks great.
A great success!
Switching on the VFD now. Everything looks normal. Nice. Oops. You can see the green LED on the Y2 stepper driver is already off, so it just shut down by itself. So these TB6600 stepper drivers are notorious for giving all sorts of problems, but fortunately my friend has a spare set of the M542 stepper drivers lying around. So what I'm going to do is I'm going to swap them out and see how the DM542 stepper drivers are going to perform. Here I made sure the micro stepping settings are correct. Old drivers out, new drivers in. So with the new stepper drivers installed, it's time to fire up the CNC JS and do some settings on the GRBL. So before you can do anything, first off, you have to make sure that your steppers are moving in the right direction when you jog it. And if your steppers are moving in the opposite direction, you can easily change the direction of your stepper motors by changing the step direction invert mask or $sign. So in my case, I'm setting mine to $sign number 3 equals to 6. So essentially I'm inverting the direction of Y and Z stepper motors. So once you have your direction correct, the next thing you will want to set will be your steps per mm, or $100 equals to an arbitrary value. So for my case, I'm using 400 steps per mm because I'm using 1/8 of microstep, which equates to 1600 steps per revolution, and I'm using a 1204 ball screw. So if you do the division, it takes 400 steps to move 1 millimeter. So once you have your travel revolution set, the next thing you will need to configure your homing cycle. For my machine, I am using homing cycle number $23 equals to 3. So from the GRBL GitHub website, you can find the homing direction. For my case, I'm using X minus, Y minus, and Z plus, which is the lower left corner. And in order to enable your homing cycle, you will need to change this $22 to equals 1 in order to enable your homing cycle. For my machine, I'm only using one limit switch on each axis, so I won't be using hard limit. Instead, I will only be using soft limits. So in order to do that, you have to change your $20 to equals 1 to enable your soft limits. Okay, so $20 equals 1. And if you're using soft limit, you will also have to set your maximum X, Y, and Z travel. So these are the values that you will have to find out for your machine. But for my machine, I found that to be about 545 millimeters for the x-axis travel, 460 millimeters for the Y and 140 millimeters for the Z axis. With your homing cycle enabled, your soft limit enabled, and your maximum travel limit for all the axes enabled, you can now start to home your machine by just clicking on the homing button, or alternatively you can just type $H. I also swapped two output spindle wires on the VFD to have it spin in the right direction. With the spindle running as intended, the next thing I want to test is the probing function. Okay, I have a DIY probe, a touch probe that is able to locate the X, Y, and Z location, the origin of the stock. So I've already got the spindle or end mill positioned just right above the probe. So with a macro which I wrote, so I will just run this macro to locate the X, Y, Z location, the origin of the stock. Once the probing is complete, I can just remove the clip and see if it goes to the stock's corner origin. So let's move the spindle to X and Y 0. Okay, and the Z to 0 as well. Seems to be just about right, so the probe is working correctly. Here I have a simple model of a rectangle with a 2D contour toolpath just to cut out the outer profile of the part, so nothing fancy here. And I've loaded this toolpath program on CNC and I have also offset the Z axis by 40 millimeters just to give it a dry run without cutting into any stock. So I have the machine homed and probed to the origin of the stock. So let's run this program. Now, however, there is an issue that I found out when I was doing the probing and also the stepper motors homing. What happened was, when I was trying to home my machine with the VFD spindle turned on, it will just trigger a hard limit alarm or a soft limit alarm, even though none of the limit switches are being pressed. And with the probing, it will go haywire as well. On the issue of the false hard limit and soft limit trigger, I had a look at my circuit again, and I did a test by decoupling the PWM to 10V analog converter wires from the Arduino board and ran the homing cycle and the probing cycle again, and it was fine. So I am very certain this board is actually giving the problem, because it is not optically isolated. The noise from the VFD is probably traveling through this board all the way back to the Arduino board, and it is messing with the limit switches. So most probably I will have to change this PWM to 10V analog converter to an optically isolated board. So but for now I will keep using this. So I will just need to home and probe the machine or the stock before I start the VFD. With a little bit of digging on the internet, I found this site called tindy.com, which sells optically isolated PWM to analog converter. So I bought two of this board just to replace my current PWM to analog board. I guess that's all I have for this episode, and I will put all the links to the reference websites and YouTube videos where I base my design on, and also links to the electrical components and the electronic components in the description below. And in the next episode, Hopefully, when my new PWM to analog board arrives, I'll be able to swap it in and test its performance. And also, I'll be doing test cuts on various materials like plastics, wood, and aluminium, and share my speeds and feeds with you guys in the next video. Lastly, before you leave, if you are getting any value out of my video and you enjoyed it, remember to smash the like button and subscribe to my channel for more contents like this. Until then, stay safe and keep making.